You can already mark a very special day in your calendars. The day when an extremely rare stellar explosion will cast a bright light on the night sky is just around the corner. We will all witness a nova, as a result of which a completely new star will appear in the sky. For weeks this star will shine brighter than anything else around it. You don't even need a telescope to witness this cosmic spectacle. You can see the nova with your own eyes. Novae are unusual stellar explosions in which huge amounts of matter suddenly explode on the surface of a white dwarf star. The explosion will temporarily increase the brightness of the star by a factor of 1500, and the reverberation of this explosion will look like a new star in the night sky for days and weeks. The amateur astronomers among you will be familiar with the constellation Corona Borealis, or the Northern Crown. Those who are less familiar with the night sky will find Corona Borealis between the better-known constellations of Boötes and Hercules. If you see some very bright stars there that almost form an arc, you are in the right place. The new star will appear within the arc from the date of the nova. White dwarfs are not normal stars. They are relics of stars that resemble our Sun but are basically already dead at the end of their fuel supply. Rather small stars collapse to form white dwarfs, which are extremely dense and hot. White dwarfs are only about the size of the Earth but have the impressive mass of the Sun. Due to their extreme density, these stars have a strong gravitational pull which they can use to suck matter from neighboring stars. A white dwarf can persist for a very long time even if it is no longer undergoing nuclear fusion. It cools slowly and often exists in this bizarre behavior during this phase, extracting matter from their surroundings. Dead stars accumulate so much mass that they explode at a critical threshold. We are familiar with this phenomenon from binary systems in which the partner star has blown up into a red giant and has thus also reached the end of its life. Compared to the white dwarf, the red giant is much wider and appears more voluminous, but it's not as dense and thus loses its mass to its much smaller but heavier companion. Mainly hydrogen is extracted, which then forms an inflammable mixture on the surface of the white dwarf. In the case of T Corona Borealis, this mixture is dissolved in a huge explosion about every 80 years. The next explosion will occur in September 2024. There is a lot of excitement. The scientific community is looking at Corona Borealis just as eagerly as we are. These days the constellation and the nova are easy to see with the naked eye, although the spectacle will take place more than 3,000 light-years away from us. Although we can witness this event virtually live, we are actually seeing something that happened 3,000 years ago. 3,000 years ago the Iron Age began on Earth. Egyptian culture began to flourish and the first cities were formed in Greece. For us, however, the nova is now a reality, as its light is now reaching the retina of our eyes or the observation mirrors of our telescopes. T Corona Borealis allows us humans to take part in this spectacle every 80 years. 3 of these novae have been very well documented to date. The oldest report dates back to the 12th century and describes the miraculous appearance of a new star in the Northern Crown. Scientists have intensively observed the white dwarf T Corona Borealis over the past decades and studied its activities in detail. Since 2015 and 2016, increasingly unusual fluctuations in brightness have been recorded. Further signs were increases in radio and X-ray emissions. The current observations are exactly similar to the activity observed before the earlier eruptions of T Corona Borealis. The last novae from 1866 and 1946 were particularly well documented, and so researchers can easily draw comparisons today. In 2018 and 2023, fluctuations in brightness caused excitement in the astronomical community. The signs were increasingly reminiscent of the patterns observed before the 1946 eruption. In 1866, scientists were still assuming the birth of a new star. The well-known astronomer William Huggins noted a nova in the constellation Corona Borealis in his records. Around 80 years later, researchers had better possibilities and recognized the increase in brightness as an explosion in a distant star system. Today, of course, we use our best telescopes to document and observe this important cosmic event as realistically as possible. In addition to telescopes, new satellites are pointed at the 2 stars around the clock. These missions record the exact amount of matter that the white dwarf is sucking in and the temperature changes on its surface. These precise measurements then allow us to make very accurate predictions as to when the critical mass will be reached and when the long-awaited thermonuclear explosion and nova will finally occur. Thermonuclear run away the power of 476 trillion hydrogen bombs. The hydrogen bomb is one of the most dangerous weapons we humans have ever developed. A medium-sized hydrogen bomb can raze an entire small town to the ground. When the nova is visible, the incredible power of 476 trillion hydrogen bombs will be detonated on T Corona Borealis. Researchers call the process that leads to this huge explosion and the brightly shining nova a thermonuclear runaway. It starts with the accretion of large quantities of matter by the white dwarf. This matter consists mainly of hydrogen. It accumulates on the surface of the white dwarf in the form of a thin layer and eventually forms an accretion disk around the white dwarf. Due to gravity, the constantly flowing matter is drawn further and further onto the surface of the white dwarf, where it's compressed and heated. The more material the white dwarf attracts, the more the pressure increases. Hydrogen and heat increasingly form an explosive mixture, and as soon as a critical quantity is reached, it goes off. Density and temperature trigger the thermonuclear runaway, and the force of trillions of hydrogen bombs is unleashed on the entire surface of the star and its surroundings. In less than a second, suddenly the brightness of the white dwarf increases by a factor of 1,500 or even more. At the time of the devastating explosion, the white dwarf T Corona Borealis will have a temperature of around 10 million degrees Celsius. Under this enormous heat, the hydrogen atoms begin to fuse into helium. This is basically the same kind of reaction that takes place in the cores of stars, but since the mass in this case is on the surface of a white dwarf, the explosion is quite different. The fusion of hydrogen to helium releases such large amounts of energy around the star in an instant that the explosion hurls the outer layers of accumulated matter into space. Then we see the first flash of the nova. As this time satellites and telescopes are pointed at the white dwarf, we may be able to experience the star's flare more precisely and up close than ever before. The extreme increase in brightness is temporary, but the nova will be visible for days or even weeks after the actual explosion. The white dwarf will slowly return to its normal brightness level. If you observe the nova, you can follow the slow dimming of the bright point of light every evening. Nova TB, you will see it clearly. It's definitely worth taking a look at this star system now before the nova. The white dwarf cannot be seen with the naked eye, it shines too faintly for that. At the moment of the nova, it will really look as if a bright new star appears from one moment to the next. Scientists are already observing every increase in brightness and documenting the changes on a daily basis. Those of you with a good telescope may already be able to recognize the flickering of T Corona Borealis. We will see the nova for days or weeks after the explosion. This new star will also be very easy to see for people without telescopes or binoculars. Even if you live in areas with a lot of light pollution, you will be able to recognize the supposed new star without any aids. During its most intense period, the nova will shine brighter than many of the brightest stars in the sky, probably shining as brightly as Arcturus or Vega. After a few days, the brightness of this white dwarf slowly begins to decrease again until the star has finally reached its normal brightness and is then barely visible to the naked eye. With telescopes or binoculars, you can see details and follow the brightness of the star over several nights. The entire event will most likely take place over 1 to 2 weeks. If you want to make a comparison, you should view the constellation before the nova, or you can watch the large star slowly burn up. The final nova star death in installments. We humans see the nova in the Corona Borealis system every 80 years. How long T Corona Borealis will continue to show this spectacle is uncertain. What is certain is that the white dwarf will increasingly lose its power. Either its last light will eventually fade, or it will explode in a final brilliant nova. A white dwarf is basically just the remaining core of a burnt-out star that was not massive enough to end up as a supernova. After the ejection of its outer layers, a compact dense star consisting mainly of carbon and oxygen remained. These stars have no way of generating their own energy through nuclear fusion, and so gradually cool down. However, as the matter in the white dwarfs is extremely dense, their enormous gravity draws matter away from the surrounding area. As a result, nova explosions may occur repeatedly over thousands or millions of years. However, once such a white dwarf has reached a magical limit, the final catastrophe occurs above the so-called Chandrasekhar limit of around 1.4 solar masses. The white dwarf can no longer remain stable. The star collapses under its own gravity and passes away as a spectacular Type Ia supernova. This supernova is extremely bright and for a few brief moments will shine brighter than all the stars in a galaxy combined. After the event, an apparently new star can also be seen which slowly disappears again, and a black hole or neutron star then forms in the place where a white dwarf once was. Become a subscriber now and be part of every new exciting video.